Okay, one last thing, students. So there is the TV diagram and the PV diagram. So what will your numericals be? Numericals will very simply be, first there will be an initial state. So look at the temperature, and if the volume is given, look at the volume, or if quality is given, so whatever it is. So when we do the numericals, we will get used to it. So let's say by looking at the temperature and the pressure. Now for example, let me give you one small example here. This is a very simple example. So your water, and water is at 120 degrees C, 500 kilopascal. That's what the question says. So, and the question is, what is it? What state is it at? So go to the table. So what tables are there? So all these numbers of saturated pressure and saturated temperatures are there in tables B1.1 and B1.2 for water. All the values of these lines and these lines are there in B1.1 and B1.2. And how do I know what is the middle line? Obviously, because this point volume is given and this point volume is given. So if wherever I am for a given temperature and pressure, I can easily determine the quality, because you know by lever rule you can do it. Very simple. I already spoke about the lever rule, because you know VF and you know VG. So when you know VF and VG, you can easily do it at whichever point they say that. So let's say they say that in the question the volume is something here, so determine what is the quality. Very easy for a certain temperature and pressure. So you can just do the lever rule, and so it will become much more clear when we do the numericals. Don't worry, right? So all these saturation pressure and saturation temperature and the volumes corresponding to VF and Vg, which is the saturated liquid volume and the saturated vapor volume, are there in tables B1.1 and B1.2. So what am I here? It's a complete liquid. All the liquid values for compressed liquid and subcooled liquid is there in B1.4. What is this? Superheated vapor. The B1.3 tables has all the temperature and the volume values for superheated vapor. So it's not just volume. You have internal energy. So first you start with volume at all these temperatures and pressure pairs. You start with volume, then you have internal energy, same thing. You have UF, UG, then you have enthalpy, and then you have entropy. That's it. That's the entire course with these phase diagrams. Got it? So if you learn to do the volume correctly, then it's just a matter of going to the internal energy and going to the enthalpy and then going to the entropy. That is all that is. So what I want to say here is, you should be very, very comfortable. Now let's say 120 degrees, 500 kilopascal for water. So you go there and look in the table B1.1 or B1.2. So what do you see for 120 degrees? You see that the saturation pressure is 198 kilopascal. Let's say 200 kilopascal. But your question said you are at 120 degrees and 500 kilopascal. So for this particular temperature, the saturation temperature is 200 kilopascal, but you are at 500 kilopascal. So have you been compressed more or have you been expanded more? So your pressure is much more than the saturation pressure. So then what state the material will be in? Liquid state, obviously. So it will be at some point here, it will be a liquid. So let's say this is a 120 degree line, correct? And this 120 degree line corresponds to what pressure? 200 kilopascal. But so I should not be drawing here. So I will draw it again, correctly I'll draw it again. So you don't need all this labeling. So now you understood in which tables you have all the values. So now I am here like this. So I am at 120 degrees. So what do? You first draw your 120 degree line. You go to the tables and you see what is the saturation pressure. Saturation pressure is 200 kilopascal. But what is the pressure that is given here? The pressure that is given is 500 kilopascal. So where would you be? You obviously have to be 120 degrees C only, but you are at 500, so you are a liquid, and you will not be having the volume of a saturated liquid. You will be a compressed liquid. So you draw a horizontal line little bit into the liquid zone, into the compressed liquid zone. So you will be somewhere here. I'll put a star there. That is where you will be. Is that clear, students? Because the temperature won't change. I drew the iso line, iso temperature line for 120 degrees. What's the saturation pressure for 120 degrees? 200 kilopascal. But what does the question say? 120 degrees, 500 kilopascal. So you're above the saturation pressure, but the temperature is still 120. So if I am above the saturation pressure, I am still 120, I would be compressed. I would be a liquid. Where would I be? Obviously 120 line, so it should be horizontal line, should come in here and into the liquid region. That's it. I hope this is clear. So now how do we write this in the PV diagram? So you said 500 kilopascal, so obviously high pressure. So you first draw the 500 kilopascal line. Then you go to the table and you see what is the saturation temperature of 500 kilopascal. It says for 500 kilopascal, it says saturation temperature is around 151 degrees. But you are not at 151 degrees. You are at a lower temperature of 120 degrees. Correct? You are at 120 degrees. So where are you? You are 500 kilopascal and you are at 120 degrees. So you will be again a liquid, because the temperature is much lower. Because what is the saturation temperature corresponding to 500 kilopascal? It's 151 degrees. So you are much lower. You are 120 degrees. So you are here. And what is the temperature that is corresponding to one? So let's write it again. So this is not the pair of saturation temperatures. So 120 degrees, the saturation pressure is around 200 kilopascal. And for 500 kilopascal, the saturation temperature is around 151. So even the temperature is lower than the saturation. So this is saturation temperature, and this is saturation pressure for 120. And for 500 kilopascal, this is saturation. So you are lower than the saturation temperature. So obviously you are a liquid. And your saturation pressure is higher than the saturation pressure. So obviously you are a liquid. So in both cases, you can easily show with a TV diagram or with a PV diagram, you can show that the material is in a liquid state. I hope I am clear. And if somebody says, can you write? So I am 500 kilopascal, I am here. So what is the saturation? So how do you go to 120 degrees from here? So I can go to one, because 120 degrees, what's the saturation pressure? 200 kilopascal. So this liquid can become a vapor only for 120 degrees if I decrease the pressure and come down to 200 kilopascals. From what value? 500 kilopascal. So you can show this line and you can show this line. But that does not happen, but you can show it. If somebody further asks the question, after you have identified this position and this position, if they say, how do you transition the liquid into a vapor? So if you want to show it in the temperature, you have to say that I am at 120 degrees and at 500 kilopascal. So I'm at a pressure much higher, so I'm here. So then how do I transition into a liquid? So for 500 kilopascal, I should see what is the temperature, 151 degrees. So I have to go from 120 to 151, reach this point, then go like this. So this is where we are at 120. I should reach 151 for 500 kilopascal, and then I become liquid. This you show it in the temperature volume curve if they ask. Otherwise you just identify the state and leave it at that. Here also you can just identify the state and leave it at that. But if they ask you for 500 on the pressure volume diagram, when will you transition? So obviously you are at a much, you're above what? Your temperature is lower than, your pressure is much higher than the saturation pressure. So what you should do, should come down from 500 to 200. So you can show how you have to come down from 500 to 200 in the pressure volume diagram. You can show how you have to increase from 120 to 151 in the temperature volume diagram. I hope this is clear, because this question that is given is not the correct pair of saturation temperature and saturation pressure. So you should go to the table calmly and you should write for 120, the pair is 200 kilopascal. Then again for 500 kilopascal, the pair is 151 degrees C. So then come to your TV diagram. First you identify your star, where you are. Then in the PV diagram you do the same thing. So now you know that you are 120, but you need to go to, for 500 kilopascal, you need to go to 151. So shoot up. Same thing. If you draw it in the PV diagram, you are at for 120 degrees. So in this case, you keep the pressure constant. In this case, you keep the temperature constant. So it's 120. But for me to become a liquid, saturated liquid, it's 200 kilopascal. But I am at 500 kilopascal. So I have to come down. So that is one more thing. You have to be very, very, very clear that when you change temperature, pressure is constant. When you change pressure, temperature is constant. But that is not a rule. There can be certain numerical problems where you can change both temperature and pressure. So don't take that as a rule and say, okay, it's pretty simple. If I keep pressure constant, then I just change the temperature so I can easily. No, it's not like that. So all I'm saying is, before I wrap this up, if I just draw the TV diagram here, so the numericals could be, I'm here, how do I get here? 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 I'm writing all the heating here. Need not be. You can have reverse direction also. Cooling. This can be the first state, this can be the second state. This can be the first state, this can be the second state. This can be first. So there is both heating and cooling. Same thing here. I can also come down like this. So temperature, you can cool. So just be careful. So this is like isochoric. This is ramp heating, ramp cooling. This is ramp heating, ramp cooling here. Ramp heating, ramp cooling. Ramp heating, ramp cooling. Ramp heating, ramp cooling. So gradual phase change is happening here. So here, if this happens, you know that the pressure has changed, because if the pressure was constant and you kept heating, how it would have gone? Like this. That is all I am saying. So there is one case that I wrote here just by chance. This can happen only if both temperature and pressure both are changing. Obviously you cannot show the change in the pressure on the TV diagram, because if the pressure was constant and if you kept on increasing the temperature, how would this go here when you are two phase? Straight like this until it becomes single phase. That's it, guys. I think this is a good start for all of you. Watch it. I'll catch you tomorrow. Bye.